The Mohr Circle is a graphical means of visualizing the stresses in an element. And for all mechanics, it is of great value, but in particular for geomechanics, soil mechanics, and rock mechanics, I think it is very useful to be able to truly understand the stress orientations and stress state inside of a body, where things like slopes and tunnels, foundations, and so on result in stresses that aren't necessarily oriented simply vertically and horizontally. So we often have to make use of stress transformations and understanding the state of stress in different orientations at a location within the ground. So I've already made a little video showing the sign convention that we use in geomechanics, but just a little bit of a reminder here. Little stress block. Compressive stresses are positive in geomechanics, and we're going to use an XZ coordinate system. And so the shear stresses, they have a name convention. The first subscript is the face on which it acts, and the second subscript is the direction. Okay. And the shear stresses on orthogonal planes are equal but opposite. So tau xz is equal to tau zx, but negative, equal and opposite. Okay, and so that's basically the sign convention that we use. This is a positive sense of shearing, okay, in general, where we have the shear stress on the positive face acting in the positive direction, and the negative face in the negative direction. So all these shears are technically an overall sense of positive shear stress. But for Mohr Circle, again, they have to be equal and opposite. Okay, so we have to define positive and negative. And I define counterclockwise shear as positive. So shear with a counterclockwise sense of motion is positive. Okay, so that would mean tau xy is positive and tau zx is negative for that stress block there. All right, so let's look at the Mohr Circle then. So Mohr Circle space, we have tau and sigma axes, and those represent the stresses on any plane. The convention I use is that negative shear is the top part of the axis and positive is the bottom part. So that's a little bit different than you're used to seeing, but that's what I've been using and what your textbook recommends. So let's just bring a little circle in there, because it's far better than one that I could draw. All right, and I'll draw another stress block over here. Draw this one bigger, so I can draw some planes inside of it to help you out. Sigma 1 and sigma 3. So we'll have the principal stresses in this case, which means there's no shear stresses, okay? Because on the principal stress planes, there are no shear stresses. All right. Now, I think one of the challenging aspects with the Mohr Circle that people find confusing is simply, first off, the definitions of these orientations. Okay, so when we are talking about sigma 1, the sigma 1 direction is acting vertically, but the sigma 1 plane is actually the horizontal plane. Okay, so that is the plane on which sigma 1 acts. All right. And of course, the sigma 3 plane is a vertical plane. Okay. One of the typical questions that you'll get with a Mohr circle is, what is the state of stress on a plane at some angle from the principal stresses? Okay, we want to know the normal and shear stress acting on this plane. Okay, we'll call it the x-plane. So we'll call that sigma x, and this tau x z. Okay, so there are some equations that you can use to figure this out. But frankly, I find that it's best to understand how this all works graphically. I think that is the best way to truly have a deeper understanding of how stresses and the planes relate to each other. So let's have a look at this Mohr circle here. Okay, so the sigma 1 value acts over here. Okay. And sigma 3, the minimum principal stress, over here. All right. So those are your maximum and minimum principal stresses. And the maximum shear stress, tau max, acts at the apex of the circle. Top and bottom equal and opposite values. Okay. And so every point on the plane represents the normal and shear stress acting on a plane in the real object to the right on different orientations. Okay. And really the main difference is that the angles between planes in the Mohr circle is twice that of reality. Okay, so for instance, in the stress block to the right, you see that the sigma 1 and sigma 3 plane are actually 90 degrees from each other. But if you look on the Mohr circle, you can see that the locations plotted for the sigma 1 and sigma 3 plane, that they're 180 degrees apart, right? So that means that theta, which is the angle on the angle used in the stress block, corresponds to 2 theta on the Mohr circle. Okay. All right. So let's get back to our plane of interest. So we want to know what point on the Mohr circle corresponds to that plane. All right, so the first thing is we can see that theta is, let's just say, about 50 degrees in a counterclockwise direction. Okay, so theta equals 50 degrees counterclockwise. 2 theta is 100 degrees. Okay. So we want to figure out 50 degrees from what and in which direction. In the stress block, you can see that it is going 50 degrees from the major principal stress plane in a counterclockwise direction. So we go over to the Mohr Circle and we go 100 degrees from the sigma 1 plane in the counterclockwise direction. And I'm just eyeballing this in here. Okay. So forgive me a little bit of inaccuracy just to demonstrate the point. Okay. 2 theta, 100 degrees. And so this point here represents the shear and normal stresses acting on the plane of interest. Okay, so that gives us the sigma x and the tau xz acting in that plane. And you can see that tau is going to be a negative value, meaning that it has so it's negative, acts in a clockwise direction, or tends to induce clockwise movement in the stress block. Okay, so I think that basically sums up the main points of the Mohr Circle. There are lots more examples of videos on the web and things like that. But I just want to make sure you get the main concepts, so you can better solve your problems in class, and really more importantly, have a good sense of this in the back of your mind for the rest of your career.